In this video we study the fundamental problem of keeping clocks synchronized in a distributed system. We assume that each node is equipped with a clock. As time passes, the clock value increases. We use integer numbers here to indicate the clock value, which is some representation of current time. As we can see here, the real time that passes between increments of the clock value is not guaranteed to be the same. These deviations occur because clocks have a limited precision, which affects their accuracy over time. In other words, the rate at which the clock value changes is itself a function of time. We assume that there is some small parameter epsilon such that the clock rate is always between 1 minus epsilon and 1 plus epsilon. Here we see the clock events at two different nodes V and W. It is easy to see that node W is somewhat lagging behind. The difference between the clock values of two nodes is called clock skew. How could we reduce the clock skew between the two nodes? The only way for W to learn about the clock skew is for node V to send node W a message containing information about its current time. Obviously, it's not so simple because some real time may pass until the message arrives at node W. We assume that there is some constant t such that all messages arrive at the latest after t time. In our model, messages are allowed to arrive instantaneously, but of course they cannot arrive before they are sent. So, all message delays are in the range from 0 to t. Note that in a network where message delays are largely predictable, the range from 0 to t can be understood as the unpredictable part of the message latency. Given this uncertainty regarding message delays, how well can we synchronize clocks? Let's consider the following scenario. The clock rate of nodes V and W are 1, that is, they advance exactly at the rate of real time. However, the clock of node V is half of t ahead. If node W receives a message containing V's time after a delay of t, node W observes that its current clock value is ahead by half of t. Similarly, if node V receives a message from node W without any delay, node V observes that its clock is ahead by half of t. Both nodes make the same observation, and so neither node knows which node, if any, is ahead. Intuitively, a clock skew of half of t cannot be prevented between neighboring nodes, that is, between nodes that can communicate directly. It can be shown that this is indeed the case. Since there can be a clock skew of half of t between all neighboring nodes on some path, the clock skew can be in the order of d times t, where d denotes the diameter of the network, which is the longest shortest path between any two nodes in the distributed system. There are clock synchronization algorithms that guarantee a clock skew in the order of d times t among any two nodes at all times, so this bound is asymptotically tight. Let's now consider a slightly different problem. Consider a node V. In the example here, node V has three neighbors, that is, there are three nodes that it can communicate with directly. There is some clock skew between node V and each of its neighbors. Since V can exchange messages with these nodes directly and the maximum message delay is t, can we ensure that the clock skew between all nodes and their neighbors is always in the order of t? Given a clock synchronization algorithm, the clock skew that can occur between neighboring nodes in the worst case is called the local skew. Intuitively, one would assume that a local skew in the order of t should be feasible. However, as we will show, this is not the case. We will show that the local skew of any algorithm grows with the diameter of the network. Given that the uncertainty about the time of neighboring nodes when receiving a message is at most t, this is a surprising result. Recall that the nodes' clock rates are always in the range 1 minus epsilon to 1 plus epsilon. For the sake of simplicity, we define that the nodes' clocks may also change at most at constant rates. The clock rate must always be at least alpha. The parameter alpha is greater than 0, which means that clocks are not allowed to stop completely at any time. Moreover, clock values may at most increase at rate beta. Let's now start with the proof of a local skew lower bound. We consider an execution of any given clock synchronization algorithm. We define that all messages arrive in half of t time and all clock rates are 1 in this execution. That is, all clock values increase exactly at the rate of real time. We consider two nodes V0 and W0 at some distance d0. We let this execution run for tau0 time, which depends on epsilon, d0, and t. Without loss of generality, we assume that the clock skew between V0 and W0 at time, tau0 is at least 0, which means that V0's clock may be ahead. We now modify the execution by changing the clock rates and message delays. The message delays are adjusted so that all messages are sent and received at the same local time so that the two executions are indistinguishable. The clock rate of W0 remains 1, but all nodes on the path to V0 run slightly faster. Node V0 has a clock rate of 1 plus half of epsilon for the duration of the execution, so it reaches the same clock value after a duration that is shorter by the same factor. Let's focus on the execution until exactly the point in time when V0 reaches the same clock value. The clock values of neighboring nodes drift apart at the difference of the clock rates, which is epsilon divided by 2 times D0, for D0 times t divided by epsilon time. We see that the difference at the end is half of t. So, every message delay must be adjusted by at most half of t in either direction, which implies that the new message delays are in the range 0 to t as desired. We conclude that it is a valid execution. Note W0 had D0 times t divided by 2 less time to increase its clock value. Since it must increase its clock value at a rate of at least alpha in this time interval, we get that the clock skew between V0 and W0 is at least alpha times D0 times t divided by 2 at the end of the considered interval. Having built up some clock skew, let's now extend this shortened execution. During this extension, all clock rates are again 1 and all message delays are half of t as before. However, we consider a duration that is some factor b shorter. The factor b is a constant that is a function of the constants, epsilon, alpha, and beta. The clock skew is reduced by at most beta minus alpha times the duration of this extension because V0 must increase its clock value at least at rate alpha and W0 can increase its clock value at most at rate beta. We choose the constant b in such a way that the remaining clock skew is at least alpha times D0 times t divided by 4. Let's now take a closer look at the execution extension. If the average clock skew is at least alpha times D0 times t divided by 4, then there must be two nodes V1 and W1 at distance D1, which is a factor of b less than D0, such that the average clock skew between these two nodes is also at least alpha times t divided by 4. Let's zoom in and examine the execution with respect to the nodes from V1 to W1 more closely. We have an execution where all clock rates are 1 and all message delays are half of t. We can now apply the same transformation as before, letting nodes closer to V1 run faster. The modified clock rates are again the same, ranging from 1 to 1 plus epsilon divided by 2. Node V1 reaches the same clock value again after a duration that is shorter by a factor of 1 plus epsilon divided by 2. It follows again that the execution is valid with message delays in the range from 0 to t. If we cut off the execution when V1 reaches the same clock value as in the previous execution, the execution is shortened by D1 times t divided by 2. As a result, we see that the clock skew between V1 and W1 at this point in time is greater than the clock skew that was built up between nodes V0 and W0. We can now rinse and repeat this same process, extending the execution, finding nodes on the path with a large enough clock skew, and then modifying the extended execution again to increase the clock skew. How large does the clock skew get? The clock skew between V0 and W0 is alpha times the distance times t divided by 2. The clock skew between V1 and W1 is at least 3 alpha times the distance times t divided by 4. If we continue in this matter, we find that the clock skew between some nodes, Vk and Wk, is at least k plus 2 divided by 4 times alpha, times the distance between Vk and Wk times t. How long can we actually play this game? How large can k get? This is a good time to pause the video and think about it for a moment. Did you figure it out? We defined that the distance between the nodes decreases by a factor b. This is true in every step, so we get that the distance between Vk and Wk is d0 divided by b to the power of k. Obviously, the distance between the nodes must be at least 1. Moreover, d0 can be at most the diameter d. We get that k can be at most log base b of d. We now have our result. No clock synchronization algorithm can prevent a local skew in the order of t times log d. Note that we used a constant upper bound beta on the clock rate, so algorithms are not allowed to instantaneously increase their clock values. It can be shown that the same lower bound holds without any restrictions on the increase of the clock values. Let's summarize what we've learned. We studied the clock synchronization problem where the goal is to minimize the clock skew between the nodes of the system. It is well known that a clock skew in the order of d times t between any two nodes cannot be prevented. In this video, we showed that it is not possible to guarantee a clock skew in the order of t between neighboring nodes by proving a lower bound of t times log d. Note that there are algorithms that match this bound, achieving an asymptotically optimal local skew. Thanks for watching.